Okay, so purpose of today's lab is that we want to basically verify and study the validity of Newton's second law in a system. Okay, now we know that in a system, all of the mass in the system accelerates together at the same rate. All right, so in this lab, what we're going to be doing, incidentally, I'm kind of telling you the variables without telling you the variables, so if you're paying attention, you'll get them. Okay, what we're doing in this lab is we're going to have this cart, and we're going to have some masses in the system. All right, so I would put some masses on the cart, okay, and I would have some masses hanging over the pulley. Okay. As the lab goes on, I'm going to move masses from the cart over the pulley, but I'm not taking them out of the system. Okay, so I'm not adding or subtracting any mass from the system. All I'm doing is changing its location. Now, I want you to think about what I'm changing when I change the location of the masses, because I'm going to tell you right now, spoiler alert, the manipulated variable is not the location of the masses. Okay? When I move a mass from the cart over the pulley, what am I changing about this system? Sorry, just for you to think about, not actually looking for anyone to answer it out loud. Okay? So, when I move a mass over this pulley, okay, it's going to change something very important about the system, but not the system's mass. Okay? What we're going to be recording in this lab is the velocity of the cart so that we can get its acceleration. Okay? So we're recording the velocity, but what we really want is the acceleration. So we're going to build a velocity versus time graph. Actually, we're going to build one velocity versus time graph with several runs on it. Okay? Each run, more mass will be over the pulley, which should cause a greater what? Right. Okay? So I'm looking for changes in velocity. I'm looking for changes in acceleration. Okay? By changing something these masses cause when they're hanging over the pulley. All right? Now, everything else between trials, including the mass of the system, is going to be unchanged. All right? You're going to use this cart, this ramp, okay, and all other conditional things to do with it. Okay? Each trial will be the same. Now, some things when you set this up that you're probably going to want to be mindful of. Okay? Owen already observed one of them. Is that when I let go of this cart, it's already on the move. Okay? So, if we're thinking possibly about sources of error or explaining results later, okay, this is probably something we should be mindful of. You do have an app on your phone that can tell you whether this is level or not. Okay? Everybody with me so far?
I don't see a sources of error.
It's evaluation at the bottom.
Oh.
It doesn't say source of error, it says eval. Yeah. All right. So, if we're looking at the hypothesis, okay, our hypothesis should go like this. Okay, the if part should talk about what Newton's second law says. Okay, in other words, what's the effect of a changing net force on the acceleration? Okay, tell me about the relationship between net force and acceleration. Okay, so if Newton's second law says blah, 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 okay, and The and part's going to briefly describe our experiment. Okay? A cart will be subjected to increasing applied force, okay, with its velocity and acceleration measured. Okay? That's essentially what we're doing here. Okay? Then tell me what you will see in terms of the rate of acceleration as force increases. And that can be in a couple of ways. You can tell me what your graph, your velocity versus time graphs are going to look like, okay, on each trial. Is it going to get steeper or shallower or whatever? Okay, so then, okay, predict your results. As you increase the applied force, what's going to happen to the acceleration? And try not to make the if part and the then part sound exactly the same, because they are talking about kind of similar things. One needs to say if, and the other needs to be a prediction. All right, so that's your pre-lab stuff. Okay, obviously I'm kind of weaning you off telling you what the variables are, okay, at this point. So the setup is going to work like this. You're going to do 4 trials. Okay? In your first trial, okay, you're going to have, I think it tells you here, yeah. Okay? So in the first trial, you're going to have this setup. The blue and the red are to tell you the mass of the blue carts and the red carts. Don't ask me why, but the carts have different masses depending on their color. I don't know why. Blue plastic is apparently lighter than red plastic. I don't know. But for whatever reason, there is a 4-gram difference between the blue carts and the red carts. Okay? So in trial number 1, okay, you're going to have the mass of the cart. So the carts are 0.274 and 0.270 kilograms. Okay, so that's 274 grams or 270 grams. But in your first trial, okay, you're going to have 670 grams on the cart. Sorry, the cart and the masses. Right? So what we have to think about here is, all right, how much extra mass am I putting on the cart in trial 1? How much extra mass? 400 grams. Okay, so it's super convenient because there's a 200-gram mass right here, and in those sets, there's 2 of them. So you can put them both on the cart. Now, a little trick with these carts. I will have to get more fun tack. Because we need fun tack. Why do we need fun tack? Make it fun. And what else? So they don't slide around. Think Newton's first law here. If I just set these things on the cart and then I drop a mass, okay, the cart's going to go where the mass is going to do. They're going to stay put because of Newton's first law. I don't want that, so I'm going to use fun tack just a little bit, just enough to stick them to the top of the cart here so they don't come off. Okay. The other thing you could conceivably do is push them towards the back of the cart where they can't slide. Okay. If they're against the back little shelf here, they also won't move, and none of the accelerations are big enough for them to go flying over the lip. Okay, but fun tack makes it more fun. So we do it that way. Okay, so I'll go get more of that as you guys are getting set up. All right, so in our first trial, okay, we're going to have 400 grams on the cart, plus the cart, and 50 grams hanging over the pulley. All right, so that's that one. Okay, so you're going to have your string tied to your cart, and the best place to tie it Okay, so the best place to tie it on is right here. There's actually a little loop, plastic loop, and that's dead center. Okay, why do I want to make sure that the force is always acting from dead center?
You don't want to pull it so it's no contrasting direction.
Yeah, if I pull it in any direction other than straight forward, okay, there's grooves here. It's going to pull it to the side. It's going to pull the wheels into the groove, and that's going to produce more Right, and I don't want that. I want to reduce friction as much as possible here. Okay, friction is obviously a component here, it's a part of this experiment, but I want to minimize it as much as possible. Okay, so I want to make sure that I'm pulling directly, because I see people and they tie it around this thing here at the front, the magnetic part. Okay, and we don't want to do that because it always ends up having either a downwards or an upwards or a sideways component to the force, okay, and that does some weird things to the experiment. So tie it onto the plastic loop, that's the best place. Okay, then you're going to put it on the track, and your best bet is to tie a loop in this part of the string, and then hang the mass from the loop. All right, so to get it going, you ever have one of those days?
No.
Okay. All right, so I'm going to have this loop, I'm going to have the mass in the loop, okay? And then I'm going to put the mass over the pulley like so, okay? This is much harder with just one person. And then I'm going to have someone who's going to be in charge of stopping and starting the cart, okay? Don't hold the mass. You want the mass to be hanging there so that everything, all the string is taut. Okay? Now, you'll notice that this isn't perfectly straight on. Possibly a small source of error there. Okay? And what I'm going to do, okay, is when the person with the timer has started the timer and is seeing the line going, because we know there's a bit of a delay there, okay, then they'll tell me go, and I'll let go of the cart. Now, there does need to be somebody with one job right at the pulley. What's their one job?
To stop it.
Yes, because if they don't, the pulley will look like this. It's not supposed to be in two pieces. Okay? There's a lot of mass there. Okay? And when it hits these very delicate but also highly efficient, almost frictionless pulleys, they will break. Okay? So make sure there's somebody with one job stopping that cart. Okay? How long does this thing need to accelerate for?
Like a second.
Yeah, we don't need a lot of time. It's going to record at 20 points per second, so it doesn't need to go very far. In fact, it can only accelerate until what? Until the mass hits the floor. Okay, so that's about how much of this I've got, right? I made my string length about right so that the distance it can fall to the floor is about this distance. Right? So when I stop it, I'd have been out of acceleration room anyway. Okay? And all the strings are about that same length, so they're all good that way. Right? So please be mindful of that. Okay, so you're going to do 4 trials. First one, 400 grams on the cart, 50 over the pulley. Second trial, okay, you'll notice we're taking 50 grams off the cart. Now, you can't just go, oh, I'll take 50 grams off the cart, because you had two 200-gram masses sitting on the cart. Right? So you're going to have to do a little bit like permutations and combinations here a little bit, okay, to get the right amount of mass over the pulley and the right amount of mass on the cart. Okay? I think you can do it with one mass set. Pretty sure. If you can't, then just grab a second mass set. Okay? All right, in your second trial, we're taking another 50 grams off the cart and putting it over the pulley. Okay? And in trial 4, another 50 grams off the cart and another 50 over the pulley. Okay, so each time, all we're doing is taking 50 off the cart and adding it to the pulley. Okay, is that pretty clear? All right. Now, when you're combining masses over the pulley, something to make note of is there's a groove on the bottom of all the masses. It's for that. Okay, rather than trying to put them all through the same loop on the string so that they're like all tangled because they inevitably come apart while they're falling. Okay, so if you hang them like this, that generally doesn't happen. That seems to work a lot better. Okay, so you can hook them up like that. And I don't think there's any situation where you'll need to have more than 3 of them. Everybody clear on what the procedure is? Before I even start talking about the analysis or the graph or anything, I want you guys to get the data. Because otherwise I'm just going to overload you. Okay, so set up a setup like this. Okay, 4 trials. 400 on the cart, 50 over, and then transfer 50 each trial till you got 4. Okay, and then we'll talk about building the graph. Somebody can use my demo set here if they want.
No?
We'll do it right here too.
If you are to the point where you are needing to start like editing your data, what you need to do is get rid of everything except for your data for your time for run 1, because that'll be your longest time. It was the slowest acceleration, and your velocities for the other 4 runs. Okay, so you'll need time for run 1, and you'll need velocity run 1, run 2, run 3, run 4. Because what we want to have at the end of all this is this. Okay, we want to have our time and our velocity data for each run. That's all we need. Okay, so hopefully everybody's at this point here where they've got their data and we now need to edit it. So open it with Google Sheets. Okay, same as we did before. And what we're going to do here is we're going to delete all the columns except the time for run 1. So this column here has to go. Oh, and I can't do that on my touch screen. Okay. All right, so what you want to do, guys, is delete everything except time for run 1, velocity for run 1, velocity for run 2, velocity for run 3, velocity for run 4. Delete everything else. Okay, those are the only 5 columns that need to remain. Time run 1 and the velocities for each of your 4 runs. That's all that needs to stay. Okay, I can't do that on the touch screen because it's just too long. Okay. What you should end up with when you're all done, okay, is this. All right? When you get to this, build a velocity versus time graph. Okay? Now I know I'm probably ahead of a bunch of you, and I apologize for that, but we're going to have to. I can't do that one here either. Okay, and so you'll get a velocity versus time graph that looks something like this. Okay, you'll go to Customize, go to Series. Okay, make sure you get trend lines in there for each one, and you'll definitely need the equation for each line. Because the slope of each one of these lines is the what? The acceleration, and you're going to need that. Okay. Just let me get through this before our class is done here. Okay, so once you've got that, guys, let's just quickly talk about the analysis here. And again, I know probably not everybody's there, but I want to make sure that we cover it. Okay, so you're going to end up with a graph that has obviously those on it. Okay, now for the analysis part, okay, the first part is the graph, Okay? The second part is calculating an applied force value and recording it in your table. It actually tells you how to do that here in the chart. What is acting as your applied force? What's pulling the cart? Right, the force of gravity on the hanging mass. That's your applied force. So you just calculate that for each trial by taking the hanging mass and multiplying it by 9.81. It does need to be in kilograms, which is why I have it in kilograms in my chart. It needs to be in kilograms in your chart as well, because a Newton is a kilogram meter per second squared. Okay? The acceleration, this is the value. You're just bringing it over from your graph. Okay? It's the slope of each line. Bring it over for each one. And then calculate your net force. That's the mass of the system times the acceleration. Theoretically, the relationship between the applied force and the net force should be what? They should be. In a perfect physical world, are they going to be? That's going to be part of your analysis. Okay? Coming up with reasons why they're not. Okay? And we talked about a few of them. So, if we're looking at the analysis here, okay, so using the formula, okay, what's the relationship between net force and acceleration? Well, I think you can see that as you increased the force, something happened. Talk about that. And then for number 6, this is probably the most important one, okay, number 5. Draw a free body diagram of the forces involved in real life, in what happened here in the lab. For that, and for number 6, because they go together. One's the diagram, one's the explanation. Okay, you need to tell me, how did these two things relate? If your net force was bigger than your applied force, explain why that might have happened. Some of you might have that. Okay, if your net force was smaller than your applied force, some of you might have that situation. Explain why. Okay, what other forces were involved? Okay, so think about, if your net force was less than this, what does that mean was going on here? If your net force was greater than this force, think about what that meant for moving along here. All right, those are the things we have to consider. And I actually did show you both of those and talk about both of those situations at the beginning of class. Think about what other forces might have been present to cause that. That's what you have to explain in question number 6 and diagram with a free body diagram in question 5. Okay? It doesn't need to be for each trial. It can be over your experiment in general. Okay, so I'm not expecting a free body diagram for run 1, a free body diagram for run 2. You would have had the same thing happen most likely in all 4 trials, so just draw it as it occurred. Okay, Tiki, question?
So what was the one that you said you wanted to, did you look at number 4 and all that? I forget.
Number 4, you're just telling me the relationship. As you increase the net force, what happened to acceleration? Okay? The 5 and 6 are the important ones. They're the diagram and the explanation of the diagram. Right? And then, as always, okay, we want to have our conclusion, copy paste your hypothesis, did what happened in the lab, support or reject your hypothesis, explain, and then your sources of error. You need 2 and ways to fix them. There's plenty of sources of error, non-human error, okay, in this experiment that you can talk about and fix. Okay.